Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. Today we are continuing the discussion on non-uniform flow. So non-uniform flow classified into gradually varied flow and rapidly varied flow. In gradually varied flow, flow characteristics, that is flow depth velocity, changes gradually over a long distance. In rapidly varied flow, this flow characteristics, that is flow depth velocity, changes suddenly over a short stretch of the channel. So one of the example of rapidly varied flow is the hydraulic jumper. The phenomenon of sudden increase in the depth of the flow due to the transition of the flow from supercritical to subcritical is called hydraulic jumper. So it is also called a standing wave or stationary wave in a channel flow. The hydraulic jump is formed at a section where low depth stream of high velocity strikes sufficient depth of liquid flowing with low velocity. So the incoming flow is supercritical state, whereas it strikes the subcritical state of flow, and hydraulic jump forms at this meeting point. So when the hydraulic jump occurs in a flow, the depth of flow increases suddenly and the flow experiences a considerable energy loss due to eddy formation and turbulence. Since the depth of flow in a hydraulic jump suddenly changes, the phenomenon can be categorized as rapidly varied non-uniform flow. Since the non-uniformity is limited to a short distance, the hydraulic jump represents a local phenomenon. The hydraulic jump also forms when the liquid flows out from a spillway. So in this case, the idea of the creating jump is to dissipate the large amount of energy that is carried by this water. Otherwise, it will score the entire downstream structure. In the next section, we can discuss about the energy loss in a hydraulic jump. Energy loss delta E equal to E1 minus E2, where E1 is a specific energy at the section 1 and E2 is a specific energy at the section 2. So delta E equal to y1 plus v1 square by 2g minus y2 plus v2 square by 2g. Since the same discharge is flowing from section 1 to section 2, v1 equal to q by a1 and v2 equal to q by a2, where a1 equal to b into y1 and a2 equal to b into y2. So this equation can be written as delta E equal to y1 plus q square divided by 2g into a1 square minus y2 plus q square divided by 2g into b square y2 square. But small q equal to q by b, that is discharge per unit width. So if you are substituting q square by b square as q square, so this equation becomes delta E equal to q square by 2g into 1 by y1 square minus 1 by y2 square minus of y2 minus y1. So this can be simplified into q square by 2g into y2 square minus y1 square divided by y1 square y2 square minus y2 minus y1. But q square by g equal to y2 y1 into y2 plus y1 by 2. So this equation represents the momentum equation of hydraulic jump in a rectangular channel. So if you are substituting q square by g equal to y2 y1 into y2 plus y1 by 2, then this equation turn into delta E equal to y2 minus y1 the whole cube divided by 4y1 by 2. So y2 and y1 are the flow depth after and before the jump. So this equation can also be written in terms of velocity as delta E equal to v1 minus v2 the whole cube divided by 2g into v1 plus v2. So you can use either of these equations for the computation of energy loss. So in this section, we can discuss about the length and height of the hydraulic jump. Length of the hydraulic jump is the distance measured from the front face of the hydraulic jump to the point on the surface immediately after the hydraulic jump. So length of the hydraulic jump is represented by Lj, that is equal to 5 to 7 times of y2 minus y1. y2 is the depth of flow after the hydraulic jump and y1 is the depth of flow before the hydraulic jump. And height of the hydraulic jump is represented by Hj. It is the difference between the depth of flow after and before the hydraulic jump. Next is the use of the hydraulic jump. One of the major use of hydraulic jump is the energy dissipator. Hydraulic jump is formed at a section where low depth stream of high velocity liquid strikes the liquid of sufficient depth flowing with low velocity. This water is coming with high velocity, so the kinetic energy of this flowing water is very high and it is capable of eroding the downstream surface. So when the hydraulic jump forms, it can dissipate a large amount of energy by eddy formation and turbulence. That means by forming the hydraulic jump, the covering at the downstream structure can be avoided. Another use of hydraulic jump is it can be used as a mixing device. Hydraulic jump forms with considerable energy loss due to eddy formation and turbulence. So because of the turbulence, mixing can be done effectively. So that is why if you want to mix chemicals or fertilizers for irrigation, you can add this in a hydraulic jump so that it is well mixed with water and can provide a uniformly distributed fertilizer throughout the field. Third use is it can be used for aerating water. Since the formation of the hydraulic jump is associated with a large amount of eddies, turbulence, it becomes aerated flow. So it can be used for purifying water. Decomposition of sludge or sewage can be done effectively by the aeration of water. So when the hydraulic jump forms in a flow, it increases the water level. So during the summer season, if the water level in the irrigation channel drops, we can create the hydraulic jump and increase the water level so that the water level is always above the sea level of the gate. So irrigation process can be continued effectively. Depending upon the magnitude of the fruit number of approach flow, the hydraulic jump in the rectangular channel classified into 5 categories. The first one is undular jump. So when the approach flow has the fruit number is in between 1 to 1.7, undular jumps formed. One of the characteristics of undular jump is liquid surface shows undulations of gradually decreasing size. Next classification is the weak jump where fruit number is in between 1.7 to 2.5. So velocity is fairly uniform and a number of small rollers appear on the surface, but at the downstream water surface is smooth. The third classification is oscillating jump where fruit number is in between 2.8 to 4.8. So the entering jet of water oscillate back and forth from the bottom of the surface and it travels downstream and damage the bed bank. Normally we have to avoid this oscillating jump. So in some situations we have to use wave suppressors and it should be designed against this oscillating jump. So steady jump is well stabilized. So energy dissipation here is between 45 to 70%. But the position of the steady jump is sensitive to tailwater. So when the tailwater, that is downstream side water depth, is more than the sequent depth, it will push the jump towards the upstream side. Whereas if the downstream water depth is less than the sequent depth corresponding to the initial water level, then it will shift the jump to the downstream side. So that is why we can say that the position is sensitive to tailwater depth. And the last classification is strong jump. So here the efficiency is higher than 85%. But the rough surface prevails and it continues for a long distance. So type of the jump is basically depends upon the fruit number of the approach flow. Now let us discuss about the characteristic parameters of hydraulic jump. The strength and loss parameters of hydraulic jump are known as characteristics of hydraulic jump. The strength of the hydraulic jump is mainly represented in terms of efficiency of the jump. That is how effectively a hydraulic jump can dissipate the available energy. So one of the characteristics of hydraulic jump is relative loss. It is defined as the ratio of energy loss to the initial specific energy before the jump. It is equal to delta E divided by E1. So figure shows that the hydraulic jump occurs when supercritical flow meets subcritical flow. So y1 and y2 are the initial and final depth. So E1 is the specific energy at the section 1, that is just before the jump, that is equal to y1 plus v1 square by 2g, and a delta E that is equal to y2 minus y1 the whole cube by 4y1 y2, where y1 and y2 are the sequent depth. So relative loss can be calculated as delta E by E1. Now efficiency of the hydraulic jump is the ratio of specific energy after and before the jump. So which is equal to E2 by E1, where E2 is the specific energy after the jump, that is equal to y2 plus v2 square by 2g. And the third characteristic is relative height of the jump. It is the ratio of the height of the jump to the specific energy before the jump. So that is equal to hj by E1. So hj is the height of the jump, is the difference between the depth of flow after and before the hydraulic jump, that is equal to y2 minus y1. So these are the main characteristics parameters of the hydraulic jump. Now today's session comes to an end. We had enough discussion about the rapidly varied flow. We also discussed about the type of the jump and the use of the hydraulic jump and the characteristics parameters of hydraulic jump. So for the time being it is enough.